All right, guys, so this is going to be our last torque problem for a little bit, at least until we start talking about simple machines. But this problem I always get a kick out of. It's a spherical boulder that's being set in motion. It sounds like something like definitely Wile E. Coyote, right? Like trying to set something in motion by rolling a boulder down. I don't know. I don't know who's doing that. You guys shouldn't be going to World's End and rolling boulders down the hill anyway. So let's just treat this one like a physics problem it is. Okay, so a couple of things that we're going to have to identify, right? First thing is the point about which this boulder is going to start to rotate once it moves. So that point is going to be right here at the ground, right? And we've seen that before with our circles and things like that. All right, our force that we're going to apply is at 53.5 degrees to that vertical radius of the boulder, okay? So we're going to say that that is going to be pushing like this. Something like that. Okay, so there's the force that we're applying to this boulder. All right, like a little person's down here pushing on it like this. Okay, anyway, and then we've got this distance. Now this says the radius of this is 1.4 meters, right? So that's the d. That's the distance across this boulder. But we don't really like d, right? We want to talk more in terms of the component of d that meets at a right angle to this force. All right? So we want to figure out what this value is, because this value is r. So we have to remember that r equals d sine theta. And we know that this angle that we talked about right here is 53.5 degrees. All right, I'd like to share with you an alternate way that you could draw this problem before we get into the guess method. All right, we're going to have the same axis of rotation. We're going to draw this r value, the d value, right, from the axis of rotation. When we say that that's straight across, like that, that's our d. We could have drawn the force being applied to the top end at 53 degrees, right there, saying that this angle between the continuation of that line and here, right, we could say that's theta. We could do that. Because all we would then have to do is extend out the line of this force, back, and find out what is the point at which this meets at a right angle, right? So essentially the same thing as what we had before, right? We're just talking about just this one component. So whichever way you want to draw this is fine with me. It doesn't really make a difference. Your professors might have different opinions, though. Okay, so getting on to the guess method now. We've got G. All right, what do we know? Well, we know D. But we'd kind of like to know what r is. So we can find r because it's equal to d sine theta. And so we can say r equals 1.4 times the sine of 53.5 degrees. And so when we do that math, we get 1.125, et cetera, et cetera. Okay, we also know the force. The force on this boulder is 1,600 newtons. All right, so our unknown is what's the torque? And so the equation is going to be, since we already solved for r, we can use the simpler version, T equals Fr. Right? If we didn't do that, we'd have to do it all together. So tau equals Fd sine theta. When we plug our numbers in, tau, we get 1,600 newtons times 1.125, etc. And then we key that into the calculator, and we get 1,800 and change. But we only want 2 sig figs, right? When we evaluate our sig figs, we got 2 here, we got 2 here. We've got 3 in our degrees, but we're going to say that boils down to 2. So in our answer, our solution, we're going to make sure that we have tau equals 1,800, and that's newtons times meters, so that's Newton meters. All right, great work. Now we know how much torque the Wile E. Coyote puts on those boulders before they go flying. All right. Have a good one.